Might have mentioned, anybody watch James Bond movies?
Yes.
Yes.
That's the next name of the next James Bond movie. Double E2 Elimination.
Oh, how was your Father's Day?
Yeah, happy belated Father's Day.
Yes.
So, the other day I was sitting on the couch and my parents were watching TV and all I heard was Casey and the Sunshine Man. I'm like, never in my life have I heard that until you said it the other day. And all I heard is Casey.
They're watching Casey and the Sunshine Band?
Well, they were on like the Me TV because we don't have cable.
The History Channel?
Yeah, on Me TV. Like,
MTV?
Me TV. It's like they play all the old shows and stuff.
Okay. All stuff.
I'm pretty sure people know their songs, they just don't know it's by them.
Yes.
Well, you know their number one song?
No.
Get Down Tonight?
Oh, that's
Get Down Tonight.
I love it when he sings.
Okay, you pass back to quiz. We'll have another quiz tomorrow. Layla?
Here.
Mary Ross?
Here.
Rachel?
Here.
Sarah?
Here.
Christy?
Here.
Joanna?
Here.
Rachna?
Here.
Asia?
Here.
Rodak? Mattia?
Here.
Alex? Here. Victoria? Stephen? Here. Madison?
Here.
Troy? Mary?
Here.
Taylor?
Here.
Okay, Mass Spec. Any questions about Mass Spec?
My biggest thing is, I guess, figuring out where to clean. Like, I know that like there can be like multiple different places, but like the most obvious place to clean, that's kind of.
There's certain cations we're going to make called benzoic cation, acylium ion, carbonyls. Group lab report due today and tomorrow. There's mass spec interpretation there. Your product was hopefully a ketone, 2-hexanone, ketone, carbonyl compound. Most common cleavage fragment formed in the mass spec for a carbonyl compound is called a what? On this page here, carbonyl compound with 5' rearrangement written, mass molecular ion equals 86. Acylium ion, right? Okay, here's the acylium ion formed from this compound. Where do you form to make cations? Other than, I mean, if it's just an alkane, you just got to make like a tertiary cation or something. Where are you going to form here? Where are you going to cleave? Cleave to put the cation on a next to a lone pair, right? If we cleave here, we can get this radical and this cation. Why this cation? Because it's next to a lone pair. That's called alpha cleavage. We could draw a resonance structure. These electrons can come here. And we can now have O triple bond to carbon. Sometimes I like to draw in the carbon of this. Now with positive is on oxygen. And this is called what type of ion? Acylium ion. You can also cleave on the other side to make another acylium ion with loss of a methyl. Here we had loss of a propyl. Okay. We should also cleave here and make a different acylium ion. They're both shown down here. Here's the one we formed. The other one was, if you cleave here, you would get this one. That's icelium ion. Let's do this one here. Three mass specs, 3 compounds. Which compound goes with which mass spec?
I think the bottom one goes with the bottom.
Okay, I would look at the compounds first, and I would say, what do we expect to cleave here? This is an ether. Where would you like to cleave here and make what cation? I like to make cation next to a lone pair. We got lone pairs. I like to make cation right here, so I'm going to cleave here. And that will give propyl radical. I'm going to leave the cation on this carbon next to the oxygen. Alpha cleavage, cation next to a lone pair. Why? We can do resonance structure. I'm not going to draw the resonance structure. Resonance, that's why this is predicted to be formed. What's the mass of this? Only the cations are going to show up in the mass spec. What's the mass of it? Well, we lost a propyl. What's propyl? 43? So this should be M minus 43. That's pretty big. What's the mass? By the way, what's the mass of each of these?
88.
They're all 88, so 88 is not going to help us determine which is which. 88 minus 43 is what? 45. So the mass of this is 45. How could we form cation over here next to a lone pair? We'd have to cleave what? No, if you cleave the methyl, you would not have a cation next to a lone pair.
One of the hydrogens.
You have to cleave one of the hydrogens off of the CH3. That would be just M minus 1. A little less common. We could show that. Up here, alpha cleavage. Where do we want to form cation? On an atom next to a lone pair. Here, how do we form cation here? We cleave here. That would give cation here plus a methyl radical. This is M minus 15. We lost the methyl radical. That should be, what, 88 minus 15? What's that, 73? 73. How else could we cleave here?
The other
We
side.
cleave on the other side. Other side would give
59.
cation there plus an ethyl radical. Ethyl radical cleaved off to leave cation here. That's 29, so this is M minus 29. 88 minus 30 is 58. That should be 59. So here I predict a 73 and 59, where up there I predicted a 45. How about down here? Next to a lone pair, want to make cation here. How do you get cation there? You cleave either one of these, that's the same thing. Cleave here, we would get cation next to a lone pair plus a methyl radical. This is M minus 15. We had an M minus 15 up here as well, didn't we? Equals 73. We also predict a 73 here. What if we cleave here? Same. Again, you could cleave an H and put cation there. Let's not do that unless we have to. Okay, 73. Do we predict a 59 here? No, so there's a difference between these. I have some different predictions. Let's look at the mass specs. Is that the top one? Looks like it. Somebody gave you some neon signs here and said 73 and 57. Don't expect neon signs on the quizzes or tests. You're going to have to determine that it's a 73. What's the tallest peak called? Base peak of 73. That means it was a predominant favorable cleavage. We're predicting favorable cleavages. Did we predict a 73? Both of these we predicted 73. But this one we also predicted 59. Is there a 59? There is not. There's 57. But it ain't 59. But hold on, we predicted 59 for this middle structure. The things that we're predicting should be showing up. Because we're predicting the best, the most predictables. I don't see a 59 in the first one. I'm very suspicious that it's the middle compound. Is there a mass spectrum with a 73 and 59?
Yes.
Oh, the second one. Again, neon signs. What about the third one? Does it show a 73 and 59?
No.
So what's the answer? The middle compound goes with the middle spectrum. Do we have a molecular ion? Molecular ion is 88. It's here. And then we get two cation fragments. Why is the 59 so much taller than the 73? That is, why is it so more common that it cleaved that way, more favorable?
Because for one of them you make a methyl radical, which is less stable.
Yes. The cation is equally stable. So you can look at the other component. Which is more stable, methyl radical or ethyl? Radicals are just like cations, they're electron poor. They're stabilized by carbon substitution. This one has a rich friend pushing electrons. More stable. Now this doesn't show up in the mass spec, but it does show up in the thermodynamic considerations. Transition state leading to this being formed is going to be lower than the transition state leading to this being formed. Thus more of this is going to be formed, easier to form. Should make sense? Okay, the top one we predicted 45, the bottom one we predicted 73. Which is which? Well, the top one shows a 73. Does the bottom one show a 73? No. We predicted a 73 for the third structure, so which spectrum is it? First one, yes. The first compound we predicted 45. And it's a base peak down here, which means it's... What's 56 for the first compound? First off, 56, is this just a plain cation? It's even. There's no nitrogen in these compounds, thus the molecular weight is even, and simple cations are odd. That ain't a simple cation because it's also even. I wouldn't worry about it. Maybe something like a Merclafferty rearrangement. But it's not a carbonyl. Only carbonyl compounds do Merclafferty. It may be some other thing. It's something we don't know how to determine. Our goal here is to match compound with spectrum. We've already done that. Back up top. Third compound, 73, there. What's the 57? Did the third compound give a 57, which is loss of what? 31? Could the third compound lose 31? Could the third compound give some other cation other than the one we showed? Can you envision some other cation? Yes, what if we cleave here and leave cation there and O-methyl radical? Now this is not alpha cleavage because we did not leave a cation next to a lone pair. But it's any type of cleavage is possible in Mass Spec. Is that cation reasonable? What's reasonable about it? It's tertiary. Tertiary cations are readily formed. What's the mass of this? Well, I mean, you can add this up, or you can subtract that. Let's just add it up. 4 carbons is what, 48? How many H's? There's 3 on each end carbon, none on the center, 9. What's that, 57? Yes. What's the 57? Cation that's being observed. It's being formed, it's being heading towards the detector, it undergoes deflection by the magnetic field, and the degree to which it's deflected corresponds to the mass. Because in physics you learn that magnetic field, mass, a charged particle is going to be deflected in a magnetic field. Degree of deflection depends on its mass. Maybe also on velocity. I'm not sure, I haven't physics in a while. But velocity is constant in the mass spec, so it's the only variable really is the mass. That can be quantified and then plotted. So we call those peaks for mass, but it's really the amount of deflection by the magnet. That's what it really is. Questions here? There are others just like this in the workbook? How are we doing with those? You have a question about one of those?
Yeah, I guess it's just like some of them, whatever, like you predict, they would still give you the same numbers, and we just kind of went over.
Which page?
The very first one, page 38.
Page 38. The mass specs look different. Yeah, I mean, all 3 mass specs look different. Compounds. Same way we just did that. Where do you expect to cleave here? What do you want to form? A cation? Yeah, so you just go through and form all your expected cations, list the mass, and then start looking for the masses over there. That's what you need to do for this type of problem. Were you able to match it?
I was able to do some, I guess I just need to, you talked about it kind of cleared up, I was just confused from yesterday. But I'll work on it and see.
Confused from yesterday?
Like I was doing it yesterday and I was kind of confusing myself, but you explained this class after I was doing it, so.
Okay. You got your book chapter as well? Hopefully you guys understand that, and I'm telling you, if you didn't know already, as you move ahead in your education, more expectation that you learn things on your own. Okay, you're going to get to some program that's going to be, okay, chapters 1 through 3, there you go. Next week, we'll discuss, see what kind of questions you have. The book is written to present it to you, to teach you. You need to learn how to read it and use it and ask questions as appropriate. Okay, that's Mass Spec. We'll see how we're doing tomorrow on it. Elimination. Elimination. Everybody got the elimination handout? Elimination reactions. Beta elimination. We're removing the beta hydrogen. What type of products can be formed? Very top on this page, this reaction, there's only one theoretical beta elimination product possible. This reaction, if you simply just show all beta elimination products possible, you would be able to show 3, not just 1. So we say there's 3 theoretically possible. That doesn't mean they're all 3 going to be formed. Actually, usually only 1 is formed. Well, major. And anytime we've ever predicted products, we've always been predicting major products. That doesn't mean some minor product can also form. Like Markovnikov is preferred. Well, maybe you get a wee bit of the anti-Markovnikov, even when we say Markovnikov is the major product. All right? But typically, 1 is going to be major. Which one of those 3, though? That's what we're doing right now. The most substituted alkene is the thermodynamic product because it's the most stable. In elimination reactions, that product is called the Zaitsev product. Thermodynamic, the most stable, the most substituted alkene of the Zaitsev product, sometimes spelled with a Z. It's always the major product in an E1 elimination. Did I underline always? Yes. But not necessarily in an E2, which can sometimes give the less substituted alkene, which is called the Hoffman product. Of the 3 above in that second reaction, which one is the Hoffman product?
The first one.
The first one. The other 2 are both considered Zaitsev products, just isomers of each other. Well, stereoisomer, E and Z. The Zaitsev product has EZ possibilities, and so they're both shown, E and Z. If we do this reaction by an E1, which will be formed? I'm sorry, I shouldn't say that yet because it's still 2 products. Zaitsev. Let's keep down here. Let's look at this reaction. If you take this guy here, this alkyl bromide, heated in water, probably going to require heating. We can get this product plus HBr. This is HBr in water, right? That's how HBr exists in water. And we made HBr. We eliminated HBr from that molecule. Everybody agrees it's an elimination reaction. HBr has left the building. Okay? You only know 2 elimination mechanisms, E1 and E2. You actually know a third, we'll never do that one in this class. Is that mechanism E1 or E2?
E1,
How do you know it's E1?
because it made a Zaitsev product. Or no? Because sometimes E2 can.
Sometimes E2 can as well. How do you know it's E1? Weak nucleophile slash base. Nucleophile and base is very similar. One takes an H, the other, one attacks an H, the other attacks something else. The key word was weak. Weak base slash nucleophile. Is water strong or weak? It's a weak base, it's also a weak nucleophile. Both of them are judged by what? What's strong bases? Anions and sp3 nitrogens. What's strong nucleophiles? Anions and sp3 nitrogens. What's the only difference between the two, really? Sterics influence nucleophiles, but sterics does not influence bases. It's weak. Water is weak, so it's going to be unimolecular. It's too weak. It's too lazy to be involved in a rate determining step. This is an E1. Got to be an E1 mechanism. Since it's E1, what's the first step of that mechanism? Ionization, Br leaving. What do leaving groups do? They go bye, bye, bye. That's how you have to assess the reaction. We're doing an E1. Okay? What product is an E1 going to give? Seitzef or Hoffman? And I underline always, right? Yes. So what are the possible products here? There's a beta hydrogen here. We can put double bond here. And that's what I showed here. What's the other product? Could you show the other possible? Theoretical. We could also remove one here, and that would look like what? Double bond here. Is this stereogenic? Does this have a stereoisomer? No. This would be called the what product? What product? Hoffman product. But this reaction gives Seitzef. I do Seitzef product here. Does this alkene have a isomer? Not stereogenic. Not stereogenic. This statement is only applicable when isomers are possible. There's no isomers possible here. If it was possible and you could show E or Z, which would this reaction give? E1 always gives the most stable alkene possible, so which would it give, E or Z? It would be E. Because if you think about it, E means your high priority groups are opposite. High priority, you're going to be larger groups. Larger groups opposite is your more stable configuration. Let's look at the intermediate here. Ionization to make this. And that's the rate determining step. Then from here, we could remove either HA or HB. Something can take the H. Either Br minus can take it or water can take it. There I showed water taking it. Take the H, electrons move in. Take the H, electrons move in. There's no difference here between the two H's. Not in this case. The water will take the H, the electrons move in. And that's your final product. And that is fast stuff. I could say more here, but we really need to move ahead before I say anything else here that makes sense at this point. What about an E2? It varies. This is the same starting material, right? How do we know this is an E2? Here's our organic, we've eliminated HBr. It is an elimination. How do we know it's E2 other than I told you?
There's a strong base.
Strong nickel slash base, because here they would call it a base, because it's taking an H. Strong base. Strong base is bimolecular. It's a bully. It's not going to wait for ionization to take place. Here I come. I'm going to stick my nose in and be involved in the rate determining step. This is the Sate-Sef product. Look at this though. And this is the rate determining step. So the base takes the H in the rate determining step. More difficult step. Look at these two H's. We call them H1, H2. Which hydrogen is more accessible?
H2.
H2 is actually more accessible. H1 is sort of buried between two methyl groups, crowded. If we use a small base, the base doesn't have any problem taking the more crowded H. And we can get the best product. Sate-Sef. You always want to get the best, the more stable product. I mean, that's the way nature is. You're going to give the more stable product. But you have to realize to get the more stable product requires taking the more buried, less accessible H. Look down here though. This base has steric hindrance. Okay? You can't put substituents on the oxygen, but you can next door. Now it's got these wings on it. Okay? If you want to get to an H back here, I can maybe slip right through here if I'm small. But what if I want to get that H and I got wings? I can't get through there anymore, right? Well, that's sort of going on here. This is a sterically hindered base, it's called. Sterically hindered strong base. It's going to have a tough time taking H1. So instead, the lower transition state, the easier reaction is for it to take H2. Because H2 is more accessible, less sterics. But if you take H2, you end up with the Hoffman product. And sometimes, and this is the case, if you use a sterically hindered base, you will typically get the Hoffman product. Not because it's more stable. It's not more stable. Sate-Sef is more stable. But it's just formed easier. And if it's formed easier, it's formed faster. And if it's formed faster, we can call it the kinetic product. Let's do two reaction coordinate diagrams, real brief. Hardly going to Let's do this real quick. Let's call this reaction A. Let's see if this works out. I've never done this before. That's A and this is B. They both start here. And they both give, well, they give two different products, right? The two products, first off, are the products higher or lower than the starting? Lower, higher or lower energy than the starting? Calculator, or you can just assess this.
Lower.
Two sigma bonds broken, we made a pi bond. Where would you put product in?
Lower.
Put it higher, right? Let's call this capital A, let's call that capital B. That's A, correct, same thing. Let's call this capital B, let's call that capital C. B is higher than A, right? We just made an alkene, pi bond. Pi bond is less stable than two sigma bonds. Where would you put C compared to B?
Higher.
Yes, even higher. Let's put this here. Okay, is there a transition state going from A to B? I meant to say intermediate. Is there any intermediate going from A to B?
No.
There's only a transition state, right? A to B, only a transition state. Let's just draw something here. Okay? A to B with a transition state. Okay? A to C. How's that going to vary? Oh, I see we got two different bases. Let's consider the base. Well, let's see if this works out. A to C. And by the way, let's label this as reaction A. Right? I think what we want to show here is for reaction B, it's going to look like, and let me redraw that a little bit. That's reaction B. Little a or little b, which reaction gives the most stable product? Little a or little b? Little a gives the best product. But little a does have a higher transition state. Why did I show the transition state higher? It's more crowded. The base has to get in there, and it's like, I'm not going to get in there unless you give me a little bit more energy and push me in there. It needs more energy to force in there. Why did I draw the transition state for the B reaction lower?
It's faster.
Because it's attacking a more accessible. It can just go do that easier. But guess what? That doesn't lead to the best product, does it? Okay, if you're driven by thermodynamics, which is usually equilibrium, which pathway is it going to take if you're driven by thermodynamics? Which means you get the best product. Pathway A. And that's called the thermodynamic product. But if you're driven by kinetics, which is just speed, fastest, which is going to be formed fastest? B, because it's easier to form. Sometimes you will get product C. What makes pathway B occur. A sterically hindered base will there's some other discussion here that could actually be a little bit confusing, but I think for what we need to know, that's enough. Just trying to explain how this is the easier transition state because we used a sterically hindered base. That becomes the easier. Okay? We are using different bases, and so I think this is not strictly. We could have other discussion here. Okay, let's move on. What's one reason you may get a Hoffman product? The base is sterically hindered. What if you wanted the Hoffman product?
You would use a sterically hindered base.
What type of base would you use?
Sterically hindered.
There you go. Okay.
That first reaction, it's not saying that that's the major product, is it?
This one?
Yeah, it's just saying that that's a possible product.
No, these are major products.
Why does it attack the sterically hindered one then? Isn't,
Because,
Would it be more
because, it's,
likely?
because it's small, it can.
but why would it attack there more than the unsterically hindered?
It wants to be the most stable.
That's a good question, and that's sort of the couple of things that are a little confusing. You might think that pathway B would always occur. That's a very good question. Even if it's small, why would it? It's still easier to attack over here,
Yeah.
even if it's small. That's why I'm not sure that this is exactly correct. There's more thinking. If I told you this was reversible, then I would say, well, it does, but then it comes back and you go over. Remember we did that with the 1, 2, 1, 4? Problem is I don't think these reactions are reversible. So there's a little something that's not quite right in my over here. And that's also where I'm changing the base. Maybe with a small base. See, I'm mixing apples and oranges a little bit here because I got two different bases. In the end, you just know, small bases can take the more hindered H to give the better product. But with a bulky base, it just can't, and you end up getting the less favorable product.
So for those then, do we assume that if it can take the hindered spot, then it will? If we're saying that that's the major product?
Yeah, small bases have no problem taking the hindered H. Only when the base gets bulky does it start taking the more accessible H.
When does the base stop being small?
Anticipated death. Hydroxide is not the smallest base you can have. This is quite sterically hindered. What if we only had 2 methyls? It's in between. You're not going to have to define. It's going to be more relative questioning.
Okay.
It's not going to be, sorry, that's a
Medium base.
that's a medium and you got it wrong. No, medium you would say, well, does it make sense if it was medium you might get mixtures? You might be taking some of this and the other. Okay, let's move ahead and see what type of questions you have maybe tomorrow on that. Okay, what's another reason you could get the Hoffman product? One we know is if you use a sterically hindered base. The other, which is even a little bit more involved, is the stereochemical requirement for an E2 elimination. In an E2 elimination, the leaving group and the beta hydrogen that is being abstracted must be coplanar. I would underline that. With anticoplanar, also called antiperiplanar, very much preferred over syncoplanar. Note that it just says preferred. It does not say it's an absolute requirement. The requirement is what? must be coplanar. There's two types of coplanar. This is showing coplanar. H and B are here. Those are actually coplanar. This is stereochemistry. Is the bromine forward or back off that carbon? Neither. It's flat on the board. It's planar, flat on the planar board. How about the H? Yes, they're both flat on the board. And about the two carbons, one is up, one's down. They're anticoplanar. If the H was here, let's do a model. Bromine green, H red. There it is on the board. Okay? That's flat. That's a plane. You see the plane there? That's flat. Okay? And they're anti. One is up, one's down. Anticoplanar. What if the bromine was like that and the H was like this?
Might not be.
It's not. I mean, if you want to call this the plane, the bromine is in the plane, but the H is not. You can put the H in the plane, but then, okay, they're not coplanar. That's anticoplanar. What do you want to call that? That's syn, or same side coplanar. Just like when we were doing conformations, we called that anti. That's syn. What's anti? It's also coplanar. Okay? What's another way to draw this? Newman. That's just where I turn this like this. The bromine's in the front, right? Up. The H is in the back, straight down. I just have not drawn the other things here, like, okay? But the Newman is a great way to see the anticoplanar. Plane is now like this. Okay? Syn coplanar. All right. Now rings, cyclohexanes, which we learned how to deal with. This Br and this hydrogen are anticoplanar, not that Br and H. First off, anti is also means trans. Which hydrogen is trans to this bromine? Of the two drawn in. That one. These two are trans. Bromine is up, the H is down. Anti means trans. If they ain't trans, they can't be transcoplanar or anticoplanar. That Br and that H are cis. Those would be cis or syn-co. Well, they can't even be coplanar, but they certainly are not transcoplanar. These two are anticoplanar. We can look at that with a model. Bromine blue. And it's axial, yeah? Straight up. And then here, this is this carbon. Okay? And this one is trans. This H is trans to the bromine, right? Let's put this here. Bromine straight up, and this is the H straight down. Okay, you see them? Are they trans? Well, look, we can make the ring flat if we drew it on the board flat, which is not right, and it's not right in my hand. Here we go. Flat ring in my hand, so that's a plane. Is the blue and the white trans? Yeah. If I put the white over here, they'd be cis. They are trans. Okay. Are they coplanar? Well, just look at that one bond there. Bromine up, H down. Is that a single plane? Or is the bromine like this? It's a little bent. You see how that's the same plane there? Forget about the rest. Okay? These are anticoplanar in this ring. Okay, here's an important thing. For this to occur, the leaving group must be axial. Let's do a ring flip. Ring flip puts the bromine blue equatorial. When it's equatorial, look at the other H's. Neither one of them are coplanar now. Hold that up. And look through there. Right through here. Is there an H over here, straight up or straight down? No. There's no H over here, straight up or straight down. So there's neither one of these H's are coplanar. They're both out of the plane compared to the bromine. Take-home message is the leaving group must be axial. Only when the leaving group is axial is there an H next door that's coplanar. Now we have one that's coplanar. Here it is. Bromine equatorial. If you look at it, neither one of these H's over here are coplanar, neither one of those are coplanar. No good. Here's the other take home. For this to eliminate, it must be in this conformation. The bromine must be axial for the elimination to take place. Okay, let's do some here. Show the expected product for each reaction. First one. Now, as we move ahead more and more today and tomorrow, we're going to have to start thinking both substitution and elimination. Both of these types of reactions have leaving groups. And so, a lot of times, both can take place. Is this first reaction a substitution or an elimination reaction? Why not substitution?
Can't be substitution because the carbon adjacent to the leaving group is too leaving group. It's not tertiary.
The leaving group is on a tertiary carbon.
In order for S and 2 to work the primary.
If this was substitution, what would be the mechanism? SN1 or SN2?
That's
SN1.
S and 2 is the smallest.
Is the nucleophile weak or strong?
Strong.
Hydroxide, be a strong nucleophile. If it was substitution, it would be SN2.
But you can't do SN2 on tertiary carbon.
But you can't do SN2 on tertiary halide. So
No.
it must not be substitution. It's elimination. Classical elimination is set up here. Is it E1 or E2? How do you know it's E2? Strong. If you got a strong nucleophile or base, it's always bimolecular. We said that on the left handout. It's either SN2 or E2. But you don't do SN2 on tertiary halide. This is E2. Okay. Well, that's good because we've been talking about E2 for the last little bit here. What's the E2 product? First off, can you show all theoretical E2 products? Like we did before, we showed 3. Let's show them all, and then let's decide which is going to be the actual major product. How many theoretical beta elimination products can be shown? There's a beta hydrogen here. We'll call it HA. Where else? Any others? Yes. There's an H here, we'll call that HB. Show the products. If we removed HA and bromine, we'd put double bond here. I'm going to draw it just like that. This carbon would have a what? A methyl and an ethyl. This carbon would have a what? A methyl and a terbutyl. But this alkene is stereogenic. We could possibly also get the other stereoisomer methyl up. What do we call this? T-butyl. This is E. This is Z. Is this Satzeff or Hoffman product? Satzeff. Satzeff. Tetrasubstituted alkene. Removing the less accessible hydrogen. If you remove HA, there's two possible stereoisomers. What if we remove HB? What would the product look like? We'd have double bond between here and here. I'm going to draw that like that. What is on this carbon over here? Terbutyl. And all that. We still have stereochemistry over here. Nothing happened over here. Does that look like the Hoffman product? Satzeff, stereoisomers of Satzeff. Hoffman, does it have a stereoisomer possible? Is that alkene stereogenic? No. Here we go. 3 possible, theoretically possible beta elimination products. Which one are we going to get? Satzeff or Hoffman? First question. Why Satzeff? It is more stable. But
Hoffman is more crowded because of the terbutyl. Or does that matter? Is, yeah, but is potassium big? Or,
Well, these products are more stable because they're tetrasubstituted. This is only disubstituted. Which one are we going to get? What's the mechanism? E2, we already said that. Okay, that's why we're doing this. Because if it, E1, what if this was E1? Which of these 3 would we get if we were doing E1?
It's always.
That'd be E1 product, right? Most stable on the board? Okay. Which one do we get? We're doing E2 though. Is the base going to have any problem taking this hindered hydrogen, HA?
no.
Smallest base possible, hydroxide, should not have any problem. And we like to take that because that gives the better products. So I'm going to get rid of that one over there. The base is not sterically hindered. You're only going to get that one if you're sterically hindered base. Which one of these we're going to get though? What's the stereochemical requirement for the elimination? The leaving group and the hydrogen must be what? Anticoplanar. Bromine and HA must be anticoplanar. How do we do this? We need to draw these with an anticoplanar. Let's get rid of this. Let's draw this in a Newman projection. We can look right through here. I recommend doing Newman projection to see this. Front carbon, Circle, circle, dot, dot. Front carbon. What do you see on the front going straight down? No, nothing's coming towards you guys. Tert-butyl. What's on the first carbon coming towards you guys? Methyl. What's on the front carbon going behind the board? Bromine. Let's look back at the next carbon. What's going straight down? Methyl is actually eclipsed with this. What's on the second carbon going towards you guys? Ethyl. It's actually eclipsed with that. And what's on the second carbon going behind the board? H. It's actually eclipsed with that. That's how it is as drawn. Everything's eclipsed. Which one is HA? Right here. Is the bromine and HA, are they anti-coplanar?
They can be.
They are coplanar. These are eclipsed. The bromine is here, the H is right behind it. The plane is like this. They're both here. I can lay a piece of paper on these two pins. That would be the plane. But are they anti compared to the carbon bond? No. What are they right now? They're actually syn coplanar. Is the transition state going to occur like this? No. They need to rotate. Let's rotate the back carbon. We want this H to be here, and you'll see it when we draw it. Let's rotate the back carbon. And now we have front carbons the same. Bromine, methyl, tert-butyl. We want to rotate this, 180 degrees. We'll put the H here. What is on the back carbon? Ethyl and methyl. Ethyl comes here, and the methyl goes here. There's two methyls. Each carbon has a methyl. That carbon has a methyl, that carbon has a methyl. Let's look at this conformation. Now the H and the bromine are anti-coplanar. There's the plane right through there. They're both sitting on that plane, and they're anti about the carbon-carbon bond is there. This is how the elimination is going to take place. The hydroxide will take the H. The electrons move in between the two carbons. We can't see the two carbons. And this gets kicked off. Here's your transition state. The double bond's now there. Here's your answer. The two methyls are on the same side. And the tert-butyl and the ethyl are on the same side. They're going to get stuck like this. Because that's how the transition state has to be. Well, it doesn't have to be that way. It's highly preferred. Remember, anti-coplanar is highly preferred over syn. It could have eliminated that way, but instead it rotates and then eliminates. And when it eliminates that way, which one of these do you get? You actually get Z. The methyls are on the same side. This is your E2 product. We can clarify E2 Sate-Sef product. How are we doing this? Using hydroxide. So we did not get the best one on the board. That's the best one on the board. It gave this one because the transition state requirement or high preference. Try the next two as we take the short 2-minute break. couple of things. First off, a lot of times I'll circle this, the H and the bromine. I'm going to do that. Just to clarify, the H and the bromine, they're anticoplanar. Now, these electrons in the mechanism, right, fall in between the two carbons. Since I can't see the two carbons, I'm not really showing that arrow there. Let me also comment on why the anticoplanar. Look right here. If the base takes the H, these electrons, if we move them here, fall in to make the pi bond. How does it look like they're coming in compared to the leading group?
I'm right behind.
Right what?
Right behind.
They're coming in, these electrons move in almost like they're coming in backside. And that's the reason for the high preference. If the base over here took this, these electrons, are these moving in backside compared to the leaving group? Not as much. And so it's again, the electrons are falling in to make pi bonds sort of backside. They're coming in, falling in this way. Okay? By the way, we've also not said this. Why backside? Remember when we drew hybrid orbitals on day one and we drew that back lobe? So we would never say it again until the end of the course. The electrons are kind of pumping into that back lobe area, and that is what leads to the breaking of the bond, the leading group being pushed off. So that's why the backside is so important, that interaction of electrons with that back lobe. All right? I hope you can see this. It's almost like these electrons are coming in backside. That's why this is highly preferred. Okay, let's look at this down here. What can you say about this? What type of mechanism we do?
It's a strong, it's still strong. So,
Substitution or elimination?
it can be or secondary, it can be SN2 or, yeah.
Could this be SN2?
It could be, this is a secondary.
Secondary, yeah. Strong nucleophile. Is this going to have any difficulties doing SN2?
Yeah.
Sterically hindered. A lot of sterics. A lot of sterics on your nucleophile are going to make it preferred just to act as a base. Are bases influenced by, as much by sterics? Not as much. Still a little bit because more accessible hydrogen, that's sterics with base. Yeah. But the substitution is really affected by sterics. Again, why? Requirement for backside attacks. When a base attacks an H, how does it attack it? Does it have to be backside? We've never discussed it. If a base attacks an H, it can attack it from any direction because the H is spherical. But if you attack a carbon and kick off a leading group, it has to be an exact orientation. And because that's more exact, sterics become more important. Sterically hindered is going to limit substitution, prefer elimination. Okay. We're doing E2, right? Because this is strong, bimolecular. All right? What's going to be the product? Why Hoffman? Sterically hindered favors Hoffman? Okay. Show the Hoffman product. product? Yep. Why did I draw this trans? So the H and the chlorine were anticoplanar, it led to this. How many H's are here? Which H is going to be removed? As drawn, HB.
Wait, which one's HB? Okay.
I don't know how to get at this. If there's two H's, you don't have to do any of that. Well, actually, you do. Actually, you can. You do. You would just do it twice, though. There's two different H's. I mean, what if there were two different H's on the back carbon, like HA and then another one?
You can pick either one.
Which one would you put anti to the bromine?
Doesn't matter.
How would you decide? It wouldn't matter. If I had a choice, I wouldn't put these two groups next to each other. These two gouged to each other, that's not good. Did you notice that? In the previous one? What if we could move another H here and these two would not be gouged? Would that be better? Yes. When you have two H's, you have a choice. When you have two H's, you're going to get the better outcome. Because they had a choice. Which one do I want to put anti to the bromine or chlorine? I'll put the one with the groups furthest apart. The only time you have to do that is when you don't have a choice. Up here, how many H's did we have over here? This is where we eliminated, right?
One.
There was only one there. Since there's only one, it's the one that has to be anti. And you're stuck with the rest. We didn't have a choice. If you have a choice, yes, that's why it's trans here. Okay. Yes, that's a Hoffman product. That'd be a good answer here. That'd be a good answer there. Oh, sterically hindered. What if this was the question? What if the question said, here's a reaction, show the Sate-Sate product? That's the question. Show the Sate-Sate product of this reaction. Go. Well, keep in mind, the question is show the Sate-Sate product. If you're taking a test and it says show the Sate-Sate product, I'd probably show the Sate-Sate product.
Big question.
Maybe it's the minor product. I don't know. Maybe it's only forming a 5% yield because it's sterically hindered. So you're right. Maybe it's the minor product. Show the minor forming Sate-Sate product. How about that? Has everybody identified the H we're removing? Right? This H right here? projection. I'm going to come over here and stand. Look through here. Front carbon, I see a methyl straight down. I see an H to the right. I'm going to call that, did we label that HA or B over there or something? I'll call this C. And what do we got? Alpha to the left. Back carbon, I see an alpha straight down. It's eclipsed with that. I see chlorine coming to my right. And we're looking at this carbon, correct? There's H going back. Means it's on my left. Here. All these are eclipsed. Got to be careful here. I got two H's drawn here. This is the one we're eliminating because it's on the front carbon. Don't confuse this H over here. We ain't doing nothing with that H. That's not a beta hydrogen. That H is on the same carbon as the leaving group. Right now, is HC and chlorine anticoplanar? No, they're actually semicoplanar. I can rotate, I'll rotate the front carbon this time. That's going to make this H go here. What's on the front here? Methyl. To make the methyl go straight up. To make the alpha come here. We didn't do anything with the chlorine. We didn't do anything with the other H. And we didn't do anything with the, what's on the back here? Got two alphas, one on each carbon. Now we see they're anticoplanar. There's the plane and they're anti about the two carbons. Now draw your product based on that. Double bond between the two carbons. Carbon over here has got an alpha and a methyl. Look at this though. The two alphas are going to be what? On the same side. They're not on the same carbon, they're on the same side. And on the other ones, this carbon's got a methyl, that carbon's got an H. You can draw that in or not draw that in. If we don't draw it in, we know it's. This is your Satesef product. And it's actually, the two big groups are on the same side, Z. Hoffman. Satesef. The transition state occurs in this conformation. The two alphas are going to be stuck next to each other when the transition state is done. Questions about this type of thing?
How did you know right away it was going to be Hoffman?
Do what?
How did you know right away that it was going to be Hoffman, not Satesel?
The base is very sterically crowded. All those wings, huge. It's going to have a tough time. HC is more crowded because HC is between an alpha and a methyl. These H's over here were more accessible. Sterically hindered base is going to have an easier time taking the more accessible H's. I would say this was going to give the Hoffman. Sometimes in different testing, some textbooks some people will say, well, this is very sterically hindered, so it's not going to do substitution, it's going to do elimination, and the elimination product is Zaitsev. I would say, well, no, hold on. It would be actually Hoffman. There is some variance in how this material is presented. Again, questions could give you information. Show the Zaitsev product. Well, then you should show the Zaitsev product, if formed. If it was formed, it would be that. It would be Z. Because we only have one H, and when you only have one H, you have to put it anticoplanar to the leaving group, and when you do that, you see that these two groups are going to end up on the same side. Because they go through this transition state. Okay, look at the one below. Then we need to move ahead. TA, triethylamine. Remember we showed that earlier, it's a tertiary amine. It's often used as a non-nucleophilic base for E2 eliminations. It's an sp3 nitrogen. It's considered strong. It's not super strong because it's a neutral nitrogen, but it's strong enough to do E2. Where are the beta hydrogens at? One is here, and it's this way, HA. We got H here, HB, and we got one here, HC. Question, which hydrogen is going to be beta eliminated? Where would you like to put double bond? Here, it would have an ethyl substituent on it, more substituent. Can you eliminate HA in iodine? Are they going to be anticoplanar? Anticoplanar can also be called transcoplanar.
No.
Is HA and iodine trans?
No.
No. If they ain't trans, they can't be transcoplanar. Which hydrogen can be transcoplanar or anticoplanar? Yes. HC. The product of this reaction is going to be here. Nothing happened here, so it's all the same. If we were to clarify which H remains here, which H remains? Yes. I did not draw an HA down here. It's still down there. We looked at this up there, right?
Which one is the forward and the back on the drawing?
Here?
Yeah,
What do you mean forward or back?
like which one is HA and HB? I just can't see it.
Oh, A, B, C.
Okay.
HC is the dashed H.
Okay.
It's the only one that's trans to the leaving group. Let's take time to draw this real quick. Chair confirmation. Iodine must be in what? Axial or equatorial? Must be axial. Here's the iodine. Next carbon, let's put the ethyl. Is the ethyl axial or equatorial? It's axial. Is the ethyl axial or equatorial?
Axial.
It's axial. The ethyl is trans to the iodine, right? Okay. That means HA is here. How is HA? There we go. Is HA and the iodine anticoplanar? No. Actually, the ethyl and the iodine are anticoplanar. What if you do a ring flip? Will this become anticoplanar? No. When this is equatorial, nothing is anticoplanar. Sorry, game over for that H. Can't do anything with it. How about the other side, the other beta hydrogens? You got two here. One of them is straight down, and one of them is like this. Which one is straight down of the two? HC. Because it's trans. These two are trans, right? Up, down. And this would be B. Of the three H's, which one is anticoplanar? C. You may not be able to see it here because the bond is sort of back. The iodine is up, the H is down. It's just like this. If I turn it like this, you want me to straighten it up. Here's the plane. It's all in the plane. The base, which is what? Triethylamine. Triethylamine. These electrons take this H, these electrons move in here, kind of backside, pick that off, the double bond goes there. There's the product of it. Try this next question on your own. Okay, from here to the end of this handout are some various miscellaneous things. When either substitution or elimination is possible, we're also going to start bringing substitution and elimination together here, which will occur. Here's one comment. Heat favors elimination. You take this and heat it with water, you're going to get typically elimination product. Could we do substitution? Sure. You could heat this with water and get a substitution product. With the water nucleophile. Wait a minute. What happened here?
Oh, it was the same thing.
Well, I was just kind of joking. What did happen?
Hydrogen.
What's the mechanism down here? Obviously, it's a substitution product, SN1 or SN2. Weak. First step. Ionization. What do we get? Carbocation. What are carbocations prone to doing? Hydride shift. Cation here. How do we get the final product? Water attacks cation, right? Boom, boom. However many steps. It's just a hydride shift in there. That's how we got the nucleophile on the other carbon. Yeah? There's an SN1 reaction. But guess what? With heat, you're going to get elimination. What's the difference in the two mechanisms? It's the same thing up to a certain point. Here's the same cation. Think about it. How do you get this? Water attacks the cation and you get a O carbon bond, right? Well, how do you get the elimination product? Instead, water or HBr or Br minus, instead of attacking the cation, we'd take the H and those move in. So you get your elimination product. This would be H3O plus, right? That's H3O plus Br minus. SN1 and E1 are the same up to the cation. And then it's just the fate of the cation. If you attack the cation, you're going to get a substitution product. Or you could do a fast beta elimination and get an alkene. That would be elimination product. SN1 and E1, they're both carbocation chemistry. But which is going to be favored with heat? Heat favors elimination. Why? Because look at it. If you eliminate, if we ignore water, one molecule becomes two. Where if you do a substitution, 2 molecules become 2. Which one has more entropy? First one, 1 molecule becoming 2. More entropy. And if you heat, you will magnify the good entropy. Because the Gibbs free energy equation is what?
Delta H minus delta S.
Plus what? T delta S. Temperature magnifies entropy. If entropy is good, and you heat, it's going to make that pathway more favorable. On the other hand, if entropy was bad, you would not want to heat the reaction. You'd be magnifying a bad term. Yes?
Why are we ignoring water in the top one but not ignoring it in the bottom one?
Because in the top one, I mean, you don't even need water. I mean, forget about it. 1 molecule becomes 2.
So you just use the heat inverse.
Or you can say 2 become 3, but I mean, water's over there, it's still over here. But it's up here, water didn't really do anything.
Didn't it act as a base and pick the beta hydrogen up? And then form.
Well, you could, or you could just have the leaving group take the H, and you really don't even need water. Again, when we first showed that reaction, you said you could do it without salt. I mean, there's no change. Water is present on both sides, so it's, but down here, water clearly reacted, and it's no longer present. Heat favors elimination. Got to be careful here. Sometimes students see heat and say, well, if you're heating, so you're going to get elimination. No. This reaction down here probably also requires heat. So maybe it's not presented exactly correct. Maybe at 100 degrees you get substitution, but at 150 you get what? More heat favors elimination.
If it's the same heat, do we just look at the entropy, like the number of molecules turning into?
If you want to judge entropy, you got to look at the number of molecules.
Will you give us the numerical temperature to determine between us and water?
Heat.
Because if you were to put heat on both of those examples, then how would you tell? Would you just show
Yeah, I mean, you wouldn't be able to tell, right?
So that's what I was saying, like, would we just be, so we wouldn't be able to tell even if we just looked at the entropy, like the number?
Just show that.
Well, I would just know that heat favors elimination. And understand why, because it magnifies the entropy term. Right here. Involvement of a good nucleophile will favor substitution, while a poor nucleophile will typically favor elimination. Look at this reaction. If you react this alcohol with HBr, you get a substitution reaction, form water. How do you make OH a better leaving group? Protonated, we have strong acid, you got a nucleophile, SN1. On the other hand, if you use HF, it's probably going to eliminate, make an alkene. Why? Br minus is a better nucleophile, right? Bigger, worse parent. Nucleophiles tend to like to attack cations and make bonds. Worse nucleophile is going to be more prone to taking the H and acting as a base. All right? Again, both of these reactions involve the same intermediate, right? You're going to protonate, ionize here. The better the nucleophile, the more prone it is to adding and making a new bond. And that's an overall substitution product. Worse the nucleophile, it's going to tend to more act as a base and take the H. If you take the H, by the way, if you took the H, you would take the one over here. Put the double bond in. Okay? By the way, which is a better base? F minus or Br minus? F minus is actually a better base, which means it's better at taking H's. So the F minus will take the H, and these electrons will move in, and that's how you get your alkene. Where the Br minus will prefer to do here. Okay? So how do you know when it is, what's the line? You don't need to know the line. You need to know the trend, not the absolute. Cl minus. What about Cl minus? What would you say about it? Would it take the H or add?
Add.
Do both. Well, what's going to be the answer, though?
We'll add.
I would never ask you the answer. I would only ask you, well, what about compared to Br minus? What's the answer? More prone to taking the H than Br minus. Relative questions. All right? Common intermediate there. Actually, a very common reaction is to take an alcohol and to eliminate it and dehydrate it. We've removed water. Very common dehydration by an E1 mechanism. What's the mechanism? Protonate the OH. It ionizes to make cation. What can attack the cation? Absolutely nothing. There's no nucleophile here. Will HSO4 minus attack the cation? No, you remember alkene chemistry? Never. We'll never attack cation. Instead, though, something will act as a base and put in the double bond. Water can act as a base. There is no nucleophile, so you have to just beta eliminate. You've got water here, right? This is an aqueous acid. Water acts as a base, takes the H, and there you go. What if water added to the cation? Go ahead. Yeah, you wouldn't get anything new. But something does happen. It goes to the alkene plus water, driven by entropy. So I mean, it's going to do something. It's going to fall apart. It decomposes. It dehydrates. On the other hand, if you do the same reaction with HI, you're going to get a substitution product. Both of these reactions have the same intermediate. I'm kind of not doing something down here. What do you know about I minus? Good nucleophile? Yeah. What do good nucleophiles do? Yeah, it's going to add here. But
Why would it not do
that's what I said. Yeah. I'm not really showing something. This should probably rearrange. Up here, you don't really need to do a rearrangement. This can rearrange, right? Mine should have shown the iodine bonded down here. Right? Get the idea? Better the nucleophile, more prone to get substitution. We've already covered this a little bit, but we can clarify. More sterically hindered base will favor elimination over substitution. Question: if you wanted to accomplish this reaction, Which base would you use?
A small one, like hydroxide.
Which base would you use?
Oh, there's choices.
Oh, what is?
Which of the three bases would you use? Yes, I would use this base here. Why? More sterically hindered, and thus it will favor what? Elimination. Substitutions, SN2, very much governed by sterics. Do we have to worry about getting Zaitsev versus Hoffman here? There's only one possible product. It's either going to eliminate or not. We never said that a sterically hindered base could not eliminate at all. Just a highly sterically hindered is going to maybe prefer the Hoffman. There is no Hoffman-Zaitsev choice here. Yes. Why not use the other two bases? What's a potential problem with the other two? No sterics. Hydroxide could eliminate. Yeah, it can eliminate, but what else could it do? It could possibly do substitution when you didn't want it to.
But the one that's sterically hindered wouldn't add on because it's sterically hindered.
SN2, very much governed by sterics. Yes. Instead of this acting as a nucleophile, it's going to instead act as a base. Attacking an H is not as nearly affected by sterics. It is a wee bit if that H is hindered, Zaitsev versus Hoffman. Clever ways to make ionization of alkyl halide to carbocation faster. Have we ever talked about making halide a better leaving group? Have we ever had to? BR is a good leaving group on its own, right? Iodine. How do you make OH a better leaving group? Prognated, which makes the oxygen positive. You can sometimes make a halogen positive, but you don't do it with acid. You don't do it with proton. Instead, you can use Lewis acid. Ag plus is a common Lewis acid. What's the definition of a Lewis acid? No, what's the definition of a Lewis acid?
Accepts electrons.
No, that's a Lewis base. Lewis bases donate electrons. They accept electrons. And it's okay to say accept because that silver is fixing to accept some. These electrons go make bond to silver. Electrons like positives, right? This looks a lot like prognating in an alcohol, except we're using a silver plus, not H plus. And since it's not H plus, it's not a Bronsted-Lowry acid, but it's called a Lewis acid. What does that give? Br silver, and the bromine is now plus. So it only has, it's only owning 6 electrons. The reason you use silver is, maybe you learned in Gen Chem, certain elements really love each other. Halogens really love silver. Makes a strong bond. Oxygen really loves phosphorus and boron. Fluorine really loves silicon. Okay? Just some that have particularly high bond strength. Now this bromine's like, okay, I got to get a lone pair back. Well, I'll take it from you, carbon, and this can ionize, and what does that lead to? Well, now you're off. Maybe you were having a little difficulty, this was not ionizing as good as, well, silver ion ionized, a lot like protonating in OH. We'll pick up here tomorrow. We'll finish this up tomorrow. A couple of good questions over here. Finishing things up. Question?
We sent out